In this section, we talk about the strain in polar coordinate. There are three components: absolute RR, the normal strain in the R direction, and absolute theta, normal strain in the theta direction, and also the shear strain, okay, absolute R theta. First, we consider the normal strain in R direction. We consider the material line in the R direction, and then how this material line elongated in the R direction. We have a material line AB here. Okay, it will have a displacement in the R direction such that it will become longer or shorter. Okay, so AB will become A prime B prime. AB here will become A prime B prime. This is the material line AB before the deformation. A prime B prime is the material line after the deformation. The deformation is due to the displacement UR and UR dr here. Okay, let me explain the relation. Here, the coordinate R represent the coordinate of the point A. Okay, R here. How about point B? Point B become R plus dr because the material line is dr. So R plus dr equal R plus dr. Okay, this one plus this one equal this one. Okay, so the coordinate of point A is R. Coordinate of point B is R plus dr. Okay, and then now point A become A prime due to the displacement in the R direction, UR. And the displacement in the R direction at point B is this one. See, this is U. U means that the displacement in the R direction, it is defined at point B. So it is expressed in terms of R plus dr because the coordinate of point B is R plus dr. So this one is U as a displacement expressed in the coordinate R plus dr. So we have AB changed into A prime B prime. Now the coordinate is R plus R from R become R plus UR because we have a displacement, change it from A to A prime. And how about B prime? B prime is the coordinate, original coordinate R plus dr here, plus the displacement. Okay, we get the coordinate, new coordinate of B prime. Now the job is we calculate the length of A prime, B prime, and AB. The length of AB is easy. AB, the length of AB is just dr. A prime, B prime is this one minus this one. Okay, and then we get A prime, B prime, the length of A prime, B prime. We use this one. And subtract with this one to get A prime, B prime. So we move this term to here, and this term to here to compute A prime, B prime. Okay, now this term and this term can cancel out each other. And to compare this term with UR, we express this term in terms of the Taylor series. So we write UR plus dr as UR plus du dr times dr, and plus du dr's second derivative times dr square. But you should write one fraction here, 1 over 2. Okay, I write here. We should add a 1 over 2 here, 1/2. Okay, this is the Taylor series expression. But dr is a very small amount, okay, a small quantity. So dr square is even smaller. So this term can be negated as a high order term. All the rest term of the all the rest of the terms in the Taylor series can be negative because dr is very small. So this one is basically equal to this one. Okay. If we have finished this, we can cancel out this term with this term. Finally, we end up with this one here. This one is this one, and this one is this one, and this one is this one. But high order term can be negative. Now, the normal strain in r direction can be expressed as a prime b prime minus ab divided by ab. Okay. A prime b prime is the length after the deformation here, minus ab is the length before the deformation. Okay. Now a prime b prime equal to this one. Okay. And a prime ab prime equal to dr. Okay. So this is ab prime. This is a prime b prime. This ab bar. Okay. This is a prime b prime bar. Okay. Now this term and this term can be cancelled out to each other, and this one can be cancelled out. So finally, we end up with this term du dr equal to epsilon rr. Here, u is the displacement in the r direction. But remember, u in fact is the function of r and theta. For convenience, we use the simplified symbol as ur. Okay, but actually, you should make a compensation theta here. Okay, to make it complete. So actually, u is a function of r and theta. In this way, the ordinary differentiation should be replaced by the partial differentiation. So the exact expression of epsilon rr is epsilon rr equal to partial u partial r. Okay. Now let us consider the normal strain in the theta direction. Okay, which is the material line. Okay, we consider the material line in the theta direction, and this material line will have a strain like this. Okay, just a classical strain. Now I emphasize that this amount of strain, this quantity, will be affected by two type of displacement. Okay, this amount will become non-zero due to v. Okay, or due to u. Okay, so u and v at the same time will create delta L over L. Okay, will create the normal strain in the theta direction. What is v? What is u? U is the displacement in the r direction. U is the displacement in the r direction. V is the displacement in the theta direction. Okay, theta direction called v. Okay, the displacement in the theta direction is named as v, and the displacement in the r direction is named u. Okay, both u and v will give us the normal strains in the theta direction. Let us consider the normal strains due to v first. We have a material point A, B, C, D. Okay, but we only consider the material line AB here. Okay, and then AB here. A pi at the point A subjected to a displacement VA. The point B subjected to a displacement B, VB in the theta direction, not in the R direction. Okay, in the theta direction. Now B subjected to a point V to a displacement VB will be carried over to the point B prime here. Okay, B become B prime and A become A prime. Okay, A become A prime, B become B prime. Okay, so we we draw the picture like this, okay, to for the shape that here we don't have enough of space. So I draw this one, this one into here, okay. So A, due to the point A, due to the displacement VA will go to A prime. Point B, due to the displacement VB will go to B prime, okay. Now, the length of A prime, B prime is not equal to the length of AB, okay, right? So this elongation will give us the normal strain in the theta direction, okay. Now let us compute this amount step by step. AB is the original length, okay, length before the deformation. What is this? We can compute it like this. AB, we want to compute the material line, the length of a material line before the deformation AB here. And AB equal to AE, this large arc, okay, AB minus BE, right? AE minus BE will give us AB, right? It's clear. AE minus BE will give us AB. So here we write it as like this. But what is AE? AE is this large arc is the length of this large arc AE is equal to theta plus d theta. This big angle, theta plus d theta times R, okay, times the radius R. Theta plus d theta times R will give us this length. So this one is this one. And how about BE? BE here, how about the length here? Okay, BE. This length equal to theta, okay, theta times R, like this, okay. So as a result, AB, the length of AB equal to R d theta because this one and this one cancel out. So AB equal to the arc AB equal to R d theta. But how about A prime B prime? How about the length of this material line? We use the same concept. A prime E, it is the last material line A prime E minus B prime E, okay, minus this term, okay. B prime E, the large arc, minus B prime E, the small arc, okay, will give us A prime B prime. Understand? So this is the expression here. Now we compute A prime E. A prime E, what is this? A prime E is this. Is AE times VA. This arc times VA, okay? AE times VA is A prime E here, okay? How about B prime E? B prime E. This arc equal to BE times plus VB, okay? This section plus this section become this big section, B prime E, right? So we have B prime E equal to BE plus VB, okay? Now we rearrange the term. This one minus this one right here, and this one minus this one right here. But look at here, AE minus BE equal to AB. Why? AE, the big arc, minus BE equal to AB, right? It's clear. AE minus this small arc, okay? Subtract this small arc equal to AB, right? So we have this result. AB equal to R d theta as before. We have already considered this effect. Now we consider the elongation due to V. It is AB arc minus A prime B prime arc minus AB arc. Okay, means that the length of A prime B prime minus the length of AB. Okay, A pi B pi is this one, the length after the deformation. AB is the length before the deformation. Okay, but now what is this? This equal this. Why? Because A pi B pi minus AB equal to this one, right? This one minus this one equal to this one. This is the relation here. Okay. Now, if you understand this, we go ahead. What is VA and VB? VA is V divided as theta plus d theta. What is VA? VA is this. But what is A? A is here. The coordinate of A is theta d theta, right? So VA is the displacement divided as theta d theta. Understand? Okay. What is VB? VB, the coordinate of point B is theta. So VB is V divided as theta. Understand? Now, if you understand this relation, we can go ahead to use the Taylor series to express this term by this term. Of course, we have negated the high order term. So this term approximately equal to this term. And this term just copy it here. And this term can cancel out. So finally, we end up with this elongation. This is the elongation due to V, the displacement in the V direction. How about the elongation due to U? What is U? U is the displacement in the R direction. Means that, see, we have a material point A, B, C, D, right? We push it along the R direction. Just like you blow bigger, you blow a balloon become bigger and bigger. Okay, so this is the skin of the balloon. It just move out outside, so it will change its position. So A, B, C, D will go to A pi, B pi, C pi, D pi. This is the motion due to the displacement in the R direction. Okay, not in the theta direction, not in the theta direction, in the R direction. Okay, now if you understand this, we say we continue. B become B pi, C become C pi, A become A pi, D become D pi. So A, B, C, D will go to A pi, B pi, C pi, D pi. Now we consider the displacement between B pi and B. We say that it is UR. Okay, UR. Point B will go to point B pi due to this displacement. This displacement is a displacement along the R direction. Okay, it is clear. Now let us look at here. We want to calculate the material line after the deformation and before the deformation. Before the deformation, it is AB, right? The length is just R times the theta, right? R, the radius times the angle will give you AB, just like this. But how about A pi B pi? A pi B pi. A pi B pi is the bigger radius, R plus UR. Okay, R plus U times the theta. This one, this the big one. Okay, this length is equal to R plus U times the theta. Okay, this one R plus U times the theta. Okay, this is A pi B pi. We have this one equal to radius times the theta. Okay, now the elongation due to U is this one subtract this one, this one subtract this one. So we put it like here and this one like here. Now we cancel out this term with this term and end up with this term. So we have two sources of the elongation in the theta direction. One is the elongation due to V, which is this. Another one is the elongation due to U, which is this. So we sum it up these two terms, this one and this one. Okay, this one is here, this one is here, and this one is here. So this is the elongation due to V. This is the elongation due to U. Okay, and then divided by the original material line. Okay, this is delta L. This is the elongation. Elongation delta L is equal to this term and this term. Divided by the original length is r d theta. Original length is AB. Okay, AB equal r d theta. Okay, so a direct computation will give us this one because the theta can be cancelled out. So in this way, we can obtain the normal strain in the theta direction easily. Now we had computed absolute theta, and also we had computed absolute RR. Now we look at the formula for the shear strain. Absolute R theta. Consider we have two material lines, okay, which are perpendicular to each other, okay, like this. After the shear strain, you have the angle between these two material lines becomes smaller. We should say that this theta, we should change this symbol from theta to phi. So phi is here, not theta. This angle is phi, okay. The angle between two material lines is phi, okay. So 90 degrees minus phi equal to absolute r theta, okay. Do some modification. Now there are two sources to create the shear strain. One is due to U, one is due to V as before. We consider the shear strain due to U. U is the displacement in the R direction, in this direction, along the radius. Okay. Now the material line AB will become A pi B pi, right? Due to the displacement in the R direction. Move in the R direction, B will move to AB pi. A will move to A pi, right? What? Due to what? Due to this displacement U theta and U theta plus D theta. Why this is called the U theta? Because we have an angle theta here. I haven't write it down, but this is the angle theta. So the displacement here is U theta, and point B, the coordinate of point B is theta plus D theta, right? Theta plus D theta, a bigger angle. So the displacement here is U as a function of theta plus D theta. Okay, now it is clear that if this one not equal to this one, means that the displacement in point B and point A are not the same, then you have the shear. Means that, for example, if you deform the right hand side a little bit, my right shoulder a little bit, your left hand side, a little bit, but this one become a lot. It become a lot, then the material line will be distorted. If you deform it in the same way, then there is no shear strain. If you deform it in different displacement, this side is with a small displacement, but this side with a very large displacement, then you become you will tilt upward. Okay, you have the shear angle. Okay, along zero. See, a little bit, a lot, a lot. So like this. Okay, so the displacement here is small and the displacement here is large. So it will give us the increment. Okay, the increment as theta. So as delta, this one subtract from here called the delta. Okay, this one. And how about the shear angle here? See, A pi B pi. We draw a parallel line here. To make the comparison, we must draw AB to here, right? We push AB to this position. AB, push it forward to here. Okay, to make the comparison. So this is the new position of AB, okay, which is different from A pi B pi, and this difference will give us the shear angle theta 1, okay. So how to compute theta 1? Theta 1 is take it as a small small triangle, right triangle. Okay, this is 90 degree, right triangle. So theta 1 equal to tangent theta 1. Okay, because we consider the small deformation theory. So theta 1 approximately equals delta theta 1, tangent theta 1, and tangent theta 1 equal to delta divided by s, right? The length s equal to AB. Okay, AB is just r d theta. Okay, AB is just r d theta. This is the radius r times d theta will give us AB. Okay, like this. S. This is S equal to AB. Okay. How about delta? Delta is just this amount minus this amount. So this one minus this one, this. Okay. So if you understand this relation, we can go ahead to compute the formula. This one can be replaced by the Taylor series. Okay. As we have done this before, this can be replaced by this due to the Taylor series. And now this term can be cancelled out with this term, okay? And this term will be cancelled out with this term. So we end up with this one, okay? So in this way, we get the shear angle theta 1. Understand? Now we consider this is the shear angle due to the displacement in the u direction. Okay. Now, how about the displacement in the theta direction? Okay, in the theta direction. Now, let us consider the material line again. We have A, B, C, D, right? Now, if the point B have a displacement in the theta direction, it will move from point B to point B pi, right? And also, point C will move from C to C pi due to the displacement in the theta direction. Okay, so VR will move B to B pi. R past dr will move C to C pi, right? Because this one and this one are not the same. Okay, so we have the shear angle. Okay. Be very careful. Be very careful. To compute the shear angle, we must have such kind of concept. See, if this material line BC, okay, move just in this way, okay, a lateral way, then there's no shear strain, right? But so if this displacement equal to CE, okay, it just rotate clockwise, counterclockwise. Then there's no shear strain, okay, like this. But because it rotates not to here, it rotates from C to C pi, over rotate. So we have the shear angle. To compute the shear angle, we must use this small triangle, okay, to help us. We draw this small triangle to here. B pi, C pi, B pi, C pi, E here. Okay, we want to compute this shear angle. Now, what is the relation? Theta 2 times dr equal to C pi E, right? Equal to this the arc length here equal to theta 2 times dr. So theta 2 equal to C pi E divided by dr, right? Okay, the arc length here divided by dr give us theta 2 is approximate to tangent theta 2. It doesn't matter. Okay, I mean this relation is not very important. This one equal to this one is important. Now, what is C pi E? What is C pi E? C pi E is C pi C minus EC. Means that this term, this length equal to this length minus this length. Once again, let me do it again. This length equal to big length minus this small length, right? This section, large section, subtract with this small section will give us this section, right? Okay, so this gives us C pi E equal to C pi C minus EC, okay? And then we can compute it one by one. What is C pi C? This big length is easy. It is the displacement in the theta direction divided by at r past dr. Why this is r past dr? Let's see. The coordinate as B is r. The coordinate as C is r past dr. This point, the coordinate of this point is r past dr, right? So the displacement defined at this point, VC, is divided at r past dr. Okay, so this we divided this V as r past dr. So like this. So this amount C pi C is the displacement is V r past dr. Is here. Okay. How about VC? VC here is r past dr times this angle. Okay, phi. Okay. EC is r past dr times phi. Okay. So this section equal to the length of this section equal to this big radius r past dr times this angle. Okay. This gives us this formula. And now, what is the relation between VR and phi? We consider this small section, okay? This one, OB pi, okay? See, B equal to move to B pi by the displacement VR, right? Okay, B plus BR equal to B pi, right? So this length is VR, and this length equal to phi times R. Phi times R equal to VR. So phi equal to VR divided by R. Okay. This is the relation we want to have. Once again, VR is this one, equal to phi times R. We move this one to here. Phi times R equal to VR. Phi times R equal to VR. Okay. So we have this phi angle can be replaced by V over R, just like this. Okay. Do you understand now? Now, if you understand, then everything is easy. And this term can be replaced by this term due to the Taylor series, as we have explained before. This term equal to this term with the high order term negated. And this term equal to this term, right? And now, this term times this term times this term equal to V. So this V can be subtracted with this V because we have minus sign here. So this term can be cancelled out with this term. So the rest will be this term and this term. Why? Because dr can be cancelled out with this one, and this one become this one. So this one become here, and this one become here, and this one become here. So in this way, we have theta 1 and theta 2, two shear angle. Okay, two shear angle created due to the displacement V and U. Okay, so we have two sources of the shear strength. Now we sum these two shear angle over. Okay, to give us the shear strength, the total shear strength. Absolute R theta equal to theta 1 plus theta 2. Okay, and this is the theta 1 and this is theta 2. Okay, and theta 1 equal to this term. This is theta 1. Theta 2 equal to this term. Theta 2 equal to this term. So this is theta 2. Okay, theta 1, theta 2. Okay, this will give us the shear strength. Okay, let us take a look at the physical meaning. Theta 1 is the material point. Okay, move to like this. Okay, move like this. And theta 2 is the material point, the material line. Move like this. Okay, one is the material line, move like this. This is theta 2 is the material line, move like this. Okay, and these two shear angle will give us the total effect of shear strength. Okay, absolute R theta.